In this session, the fundamental concepts of geographic information systems, GIS, and ecological planning will be examined. First, the concept of GIS and its conceptual framework will be introduced, followed by an overview of the basic components and spatial data types of GIS. The session will then address the concept of ecological planning by discussing its purpose, core principles, and the reasons it requires a multi-layered and process-oriented approach. Subsequently, the key needs and stages of the ecological planning process will be examined. Finally, the roles of GIS across different stages of the ecological planning process will be explored by linking specific GIS capabilities to planning tasks, demonstrating how GIS functions as an analytical and decision support infrastructure. Subsequently, the key needs and stages of the ecological planning process will be examined. Finally, the roles of GIS across different stages of the ecological planning process will be explored by linking specific GIS capabilities to planning tasks, demonstrating how GIS functions as an analytical and decision support infrastructure. Within the scope of this course, the fundamental conceptual framework and working principles of geographic information systems, GIS, are examined. At the beginning of the course, GIS is introduced by explaining what it is, its main components, and the types of data it works with. In the following part of the course, the concept of ecological planning is defined, and its fundamental objectives, requirements, and processes are discussed. The different stages of the ecological planning process are explained, and the ways in which these stages are linked to GIS functions are examined. In this context, the role of GIS in the integrated analysis of environmental data, the identification of spatial patterns, and the support of planning and decision-making processes is emphasized. Finally, the contributions of GIS to ecological planning processes are evaluated, and the importance of GIS in developing sustainable, resilient, and environmentally responsive planning approaches is summarized within a general framework. In this context, the role of GIS in the integrated analysis of environmental data, the identification of spatial patterns, and the support of planning and decision-making processes is emphasized. Finally, the contributions of GIS to ecological planning processes are evaluated, and the importance of GIS in developing sustainable, resilient, and environmentally responsive planning approaches is summarized within a general framework. Analyze how GIS capabilities support the ecological planning process by linking specific GIS functions to different planning stages. What is GIS? Geographic Information Systems, GIS, are an integrated information system that enables the creation, management, analysis, and visualization of spatially referenced data. The key feature that distinguishes GIS from conventional mapping tools is its ability to integrate location-based information, where, with descriptive attribute information, within a single framework. In this way, GIS not only identifies where objects are located, but also reveals their characteristics and how they spatially relate to one another. Through this capability, GIS transforms spatial data from a passive representation tool into an analytical and queryable information infrastructure that supports deeper understanding and informed decision-making. GIS supports the entire spatial decision-making process by enabling the systematic handling of geographic information. It begins with the collection of spatial data from multiple sources such as satellite imagery, GPS, and field surveys, and continues with the organization and management of this data to ensure consistency and accessibility. GIS then allows spatial data to be analyzed in order to identify patterns, relationships, and interactions that are not visible through non-spatial data alone. These analytical results are communicated through maps, models, and spatial visualizations, making complex information easier to interpret. Ultimately, GIS transforms data into actionable knowledge by supporting informed decision-making in planning, environmental management, and policy development. GIS transforms spatial decision-making from intuition-based approaches into evidence-based processes. By making complex and multi-layered spatial relationships visible, it enables the integrated evaluation of environmental and spatial data. GIS also allows alternative planning scenarios to be tested in advance, making it possible to compare risks, sensitivities, and opportunities across space. As a result, planning decisions supported by GIS become more transparent, traceable, and defensible. This visual illustrates the fundamental components that enable geographic information systems to operate as an integrated framework. GIS should not be understood merely as a software tool, but as a comprehensive system composed of several interrelated elements that function together. Hardware provides the physical infrastructure required for the processing and storage of spatial data. Software refers to the programs and applications that allow spatial data to be managed, analyzed, and visualized. Geographic data constitute the core input of the system and include both spatial and attribute information representing the natural and built environment. Personnel represent the human dimension of GIS, encompassing the individuals who operate, manage, and interpret the system and its outputs. Organizational management supports GIS through strategies related to system implementation, coordination, and long-term maintenance, ensuring that GIS functions effectively within institutional and planning contexts. Together, these interconnected components enable GIS to function as a robust, flexible, and reliable analytical infrastructure, supporting spatial analysis and informed decision-making processes. In this slide, vector data, one of the fundamental data types used in geographic information systems, GIS, is examined. Vector data represents geographic features spatially through the use of points, lines, and polygons. This form of representation is preferred particularly for spatial features whose locations and boundaries are clearly defined. Within a GIS environment, vector data is widely used to model discrete spatial objects such as roads, parcels, rivers, buildings, green spaces, and administrative boundaries. For example, a road is represented by a line, a building or a park area is represented by a polygon, and features such as trees or bus stops are represented by points. In this way, both the location and the geometric form of spatial features are explicitly defined. One of the most important characteristics of vector data is that each spatial feature is linked to an attribute table. Through these tables, descriptive information such as land use type, area size, ownership status, and functional characteristics is stored and can be queried. As a result, GIS becomes an analytical system capable of responding not only to the question of where, but also to what and how. In this slide, raster data, the second fundamental data type used in geographic information systems, GIS, is examined. Raster data represents space as a continuous surface that is divided into a regular grid of cells or pixels. Each pixel contains a single numeric value, which represents the characteristic of the area covered by that cell. This data structure is particularly suitable for representing continuously changing environmental phenomena. Variables such as elevation, temperature, land surface temperature, vegetation density, NDVI, rainfall, and soil moisture are commonly modeled using raster data. Unlike vector data, which focuses on discrete objects with clear boundaries, raster data is used to describe gradual spatial variation across space. In the context of ecological planning, raster data plays a critical role in understanding environmental processes and spatial patterns. It is widely used in analyses such as topographic modeling, hydrological analysis, climate assessment, vegetation analysis, and risk mapping. Raster layers provide the environmental context within which planning decisions are evaluated. Together with vector data, raster data forms the analytical foundation of GIS. While vector data defines planning units and spatial boundaries, raster data provides the continuous environmental information required to assess ecological processes, sensitivities, and risks. In this way, raster data supports evidence-based and environmentally informed planning decisions. Ecological planning is a planning approach that integrates biophysical and socio-cultural information into decision-making processes, taking into account the capacities and limitations of natural systems. This approach aims to produce more appropriate, sustainable, and rational decisions regarding land use and resource management by considering the relationships between human activities and the natural environment. According to Steiner, planning is a process that translates knowledge into action. Ecological planning, however, grounds this process in ecological principles, considering natural and social systems together. Therefore, ecological planning is not merely an approach focused on environmental protection, but offers an analytical decision-making framework for determining which land use is appropriate where, to what extent, and under what conditions. In this context, Ecological planning is defined as a phased and process-based method that includes understanding the structure and functioning of natural systems, identifying environmental opportunities and constraints, evaluating different land use alternatives, supporting planning decisions with long-term monitoring and feedback. The fundamental objective of ecological planning is to ensure that spatial decisions do not exceed the carrying capacity of natural systems. This approach aims not only to protect natural resources but also to maintain and enhance the continuity and quality of ecosystem services. By placing water, soil, climate, biodiversity, and ecosystem functions at the core of the planning process, ecological planning seeks to establish a balanced relationship between human activities and natural systems. In this context, spatial decisions are directed toward reducing risks, increasing resilience to environmental uncertainties, and supporting the development of sustainable settlements in the long term. Consequently, ecological planning emerges as a holistic planning approach that focuses not only on environmental protection but also on creating safe, resilient, and sustainable living environments. Ecological planning addresses complex environmental and spatial challenges by aligning human activities with natural systems. To do this effectively, it requires several fundamental needs. To achieve this effectively, it requires a comprehensive understanding of natural systems such as ecosystems, habitats, hydrology, soils, climate, and topography as interconnected components. This approach depends on the integration of multi-layer spatial data, where environmental, social, and physical information are evaluated together within a shared spatial framework. Identifying environmental limits and critical thresholds, including carrying capacity, ecological sensitivity, and risk areas, is essential to guide planning decisions. Ecological planning also requires anticipating the potential environmental impacts of proposed actions before implementation, developing and comparing alternative planning scenarios, and supporting decisions through measurable indicators and spatial analysis. Finally, continuous monitoring and adaptability are fundamental, ensuring that planning processes respond to changing conditions and newly available data over time. The ecological planning process begins with identifying key problems and opportunities, during which the main challenges, potentials, and planning objectives for the area are defined. This is followed by local and regional inventory and analysis studies that document the natural and cultural characteristics of the area, providing a comprehensive understanding of its ecological, spatial, and socio-environmental context. Based on this knowledge base, detailed studies focusing on specific issues are conducted, and strategic planning concepts and alternative planning approaches are developed. These concepts are then translated into concrete spatial and landscape proposals, and different design scenarios are tested and evaluated. An essential stage of the process involves presenting the plan to the public and relevant stakeholders to incorporate feedback and assessments. Finally, the plan is implemented, and its performance is continuously monitored, allowing for necessary adjustments and updates to ensure the long-term effectiveness and adaptability of the planning process. Ecological planning involves working with multi-layered data, environmental thresholds, alternative scenarios, and dynamic processes that change over time. Managing such complex and interconnected systems cannot be achieved through manual or purely intuitive approaches alone. An effective planning process requires the integration of diverse datasets, systematic spatial analysis, the comparison of alternative scenarios, and continuous monitoring after implementation. At this point, the need for analytical tools becomes evident. This is where geographic information systems play a central role, providing the essential analytical and decision support infrastructure required to manage the complexity of ecological planning. In ecological planning, GIS functions as more than a technical mapping tool. It acts as an analytical and decision support framework that adds value at every stage of the planning process. By revealing spatial relationships between natural systems and human activities, GIS helps planners identify constraints, opportunities, and conflicts within the landscape. It enables the evaluation of alternative land use and design scenarios, supports risk-sensitive and resilience-oriented decisions, and improves transparency by translating complex analyses into clear spatial representations. Through continuous monitoring and data integration, GIS also supports adaptive planning, ensuring that ecological decisions remain responsive to changing environmental conditions. GIS supports the ecological planning process not only by providing data, but also through its analytical capabilities that enable a holistic understanding of complex systems. Data integration and multi-layer analysis. In the early stages of ecological planning, the most critical requirement is the integrated evaluation of environmental, social, and spatial data produced from different sources within a common spatial framework. In this context, particularly during the identifying problems and opportunities stage, the joint interpretation of diverse environmental, social, and spatial datasets plays a key role. In the subsequent regional inventory and analysis and local inventory and analysis stages, geographic information systems integrate topography, hydrology, land use, ecosystems, and socio-spatial data within a shared geographic reference system, enabling a holistic analysis of complex environmental relationships. Through this multi-layered structure, spatial patterns become visible, problem areas and potentials are analytically identified, and a data-driven foundation for the planning process is established. Sensitivity, suitability, and risk assessment. Sensitivity, suitability, and risk assessments in ecological planning aim to scientifically identify environmental constraints, vulnerabilities, and land use limitations of natural systems. Within this framework, during the regional inventory and analysis and local inventory and analysis stages, GIS evaluates multiple environmental layers together to determine areas that should be protected, areas exposed to risk, and locations suitable for different land uses. These assessments are further refined in the conducting detailed studies stage, where ecological thresholds, carrying capacity, and environmental constraints are defined in greater detail, ensuring that planning decisions remain consistent with ecological realities. Scenario development and impact evaluation. Scenario development and impact evaluation enable alternative planning approaches to be tested and the potential environmental consequences to be compared prior to implementation. This capability becomes particularly prominent from the conducting detailed studies stage onward and plays a decisive role during the creating planning concepts and design research phases. GIS models alternative spatial planning scenarios and analyzes their potential environmental impacts, allowing planning decisions to be developed based on predictive and comparative evaluations rather than intuitive judgments. Decision support and transparency. Decision support and transparency ensure that analytical outputs generated during the planning process are translated into clear, traceable, and well-justified decisions. In this regard, GIS contributes to the defining goals stage by supporting the formulation of planning objectives based on spatial evidence. In later stages, particularly preparing the landscape plan and citizen assessment, analytical results are communicated through maps and indicators, enabling planning decisions to become transparent, accountable, and supportive of participatory decision-making processes. Monitoring and adaptive management. Monitoring and adaptive management aim to evaluate planning decisions after implementation and to update the planning process based on newly acquired data. This approach is supported by GIS starting from the implementation stage and continuing throughout the management and monitoring phase. Environmental changes are tracked over time, new data provide feedback to the planning process, and planning decisions can be adjusted when necessary, transforming ecological planning into a dynamic and learning-oriented process. Geographic Information Systems, GIS, are computer-based systems that enable the collection, storage, and analysis of spatial data. GIS addresses the processes of capturing, storing, controlling, processing, analyzing, and visualizing geographic data related to the Earth's surface within an integrated framework. In this respect, GIS is not merely a mapping tool, but a comprehensive system in which hardware, software, data, and users work together to manage spatial information and transform it into informed planning decisions. The ecological approach defines planning as a holistic framework that considers the interrelated dynamics between humans, nature, and the built environment, aiming to produce systematic solutions to the challenges arising from these relationships. Within this context, ecological planning integrates biophysical, such as topography, hydrology, soil structure, climate, and vegetation, and socio-cultural data to identify land use opportunities and constraints, while supporting sustainable planning decisions that ensure the long-term protection of natural systems. At the core of this approach lies Ian McHague's principle of designing with nature. McHague's method, based on the overlay of multiple geographic layers, such as topography, soil, hydrology, and vegetation, established the scientific foundation of ecological planning and paved the way for the development of GIS. However, due to the limitations of human perception, manual and hand-based analyses become insufficient beyond a certain level of complexity. In particular, when multiple environmental layers must be evaluated simultaneously, managing large and multi-layered environmental datasets becomes increasingly difficult, the risk of error increases and decision-making processes slow down. The integration of GIS into planning processes largely overcomes these limitations. GIS enables rapid, accurate, and model-based analyses, allowing planning decisions to be produced with greater precision, realism, and predictive capacity. In this way, GIS provides a strong decision support infrastructure for more effective, sustainable, and ecologically coherent planning practices. Within this framework, the visual illustrates how the ecological approach guides the planning process and why GIS plays a critical role within it. Ultimately, ecological planning evolves into an approach that generates holistic and sustainable decisions in harmony with natural systems, marking a disciplinary shift from competing with nature to designing with nature. In conclusion, GIS should not be understood merely as a technical or mapping tool. It represents a way of thinking about space, data, and decision-making. In ecological planning, GIS functions as an analytical and integrative framework that enables complex environmental systems to be interpreted in a systematic manner. By linking data, analysis, and spatial representation, GIS supports evidence-based, transparent, and responsible planning decisions. In this sense, GIS reshapes planning practice by shifting it from intuition-driven judgments toward analytical, process-oriented, and adaptive decision-making. Within the scope of this session, what GIS is and how it works has been explained. The core components and data types of GIS have been addressed. The principles, fundamental needs, and stages of ecological planning have been examined. Finally, how GIS capabilities align with the different stages of the ecological planning process has been demonstrated.